Hi, and welcome back to Giving Shapes to Blobs. This is the last of our three-part series, and we hope you've enjoyed yourself so far. Before we get started today, I'd like to name a few concepts that we'll be making use of, just so that you can be prepared for what's about to happen. Certainly, there are some topology concepts from previous videos. In particular, you should know what the definition is in terms of open sets. Also, just recall the definition of closed sets, because I'll be using those as well. A closed set is just the complement of an open set. You should also know how to build topologies, so you should know what a basis for a topology is. Well, you should also know some examples. So you can find examples in exercises and in previous videos. The examples that come up most often are, well, first and foremost, the real line. This is just the number line with all the usual numbers in it, except with all the numbers in between as well. And just to remind you, the basis for the topology on the real line is just all of the open intervals. There's also the upper set topology, and there is multiple of these. I think the one that we'll be using most often is the one on the natural numbers. This is just, so the open sets in this topology are just of the form m off to infinity, which just consists of m, and then m plus 1, and then m plus 2, and so on and so forth. In addition to the upper set topology on the natural numbers, it's also kind of useful, and it's going to be important today to be comfortable with the cofinite topology. On the natural numbers as well. And this has closed sets are the finite sets. So all of the open sets are those sets whose complement are finite. And finally, the Cantor set. So I don't think I used the name Cantor set in a previous video, but you should recognize this one. It's just all the sequences of zeros and ones. And the open sets, the basic open sets, are those sequences of zeros and ones that start with a given word. Okay, today we're talking about continuous functions. This is probably the central concept in topology. Well, I'm very excited that we're finally here, and there's lots of pretty things that we can do with continuous functions. So in this video, I'm basically going to give you the definition. In the next video, we're going to be using them, so applying the definition to a specific kind of topological space. And these spaces that we'll be considering in the next video are called connected spaces. And finally, in the very last video of our whole sequence, Angela is going to talk about topology in the broad strokes. And in particular, the concept of homeomorphism, which is topology's version of isomorphism or equivalence. So just because because I'm going to be talking about functions this whole time, I figured I should probably just reintroduce you to what a function is. Many of you have probably seen this in math class already. So starting with an example, just given any natural number, there's one and only one number, which is twice that natural number. This probably seems kind of silly, but there is one and only one. That is the key concept to functions. So a function is a sort of transformation which takes in something and outputs a unique thing which is based on that thing. This is the definition, and I'm going to restate that in a second here. So a function is just a transformation which takes each point or element of one set to a unique element of the other set. And this is an example I'm going to be considering again and again and again. You can see that A gets sent to 3 and only 3. If A was somehow sent both to 3 and 2, this would not be a function, but it isn't. It's only sent to 3. And so we call 3 f of A, and this is well defined. You might notice that B also gets sent to 3. So 3 is also f of B. And similarly, 4 is f of C. Okay, so enough about functions on their own. What happens when a topology gets involved? Well, there's really only one rule when it comes to continuity of a function. And it's basically just that you can't tear open sets in half. So here I have a topology on the left on X. Its open sets are the sets A, B, and C. And the open sets on the right are 3 and 4, 5, and the union as well. So an example of a function tearing an open set in half can be found by just changing where A goes. Now, since these are topologies and I don't really care about the actual labels on the sets, it's a little bit easier to see this with just points instead of labels. Okay, an example of a non-continuous function, so a function that actually tears an open set in half, would be something like this. So you should notice that this open set on the left consists of 2 points. One of them gets sent to an open set over here on the right, and the other one gets sent somewhere else. So in this sense, this function f is tearing this open set in half, and we don't want that. We don't want any tearing in our continuous functions. So no tearing allowed. This first function that we were considering is much, much better with these two topologies. Okay, so how do we actually tell if an open set has been torn in half? Well, it actually lies in the target space, so the space on the right, where the function descending points to. It's easiest to check on this side. So take an open set, and this should work for every open set. Take an open set and trace it back along the function. So just look at all of those points that get sent into that open set. So here I've got this really nice example of a 1-point open set, and I can look at the 2 points that get sent to it. Well, if the function isn't tearing open sets in half, then this open set should come from an open set. In other words, the inverse image of an open set should also be open. Okay, so now since this should happen with all open sets, let's actually check a different open set and make sure that this function is continuous. So, right, yes, open sets should turn into open sets in the pre-image. Yeah, tracing back a function should give open sets from open sets. Okay, so now let's check this open set down here. This open set that consists of 2 points. It seems kind of weird to actually trace the function back, right? Because only 1 point actually gets sent into this open set. But actually, now that I say it like that, that's kind of fine, right? Tracing back the function, tracing back this open set along the function should only really produce that 1 point. So here I am tracing back this set, this 1 point in the set that actually comes from a point in X. Well, this is also an open set. And so we have successfully checked that this function that I've got on the screen here is actually a continuous function. Okay, so let's actually think about defining what it means for a function to be continuous. There's kind of an intermediary step. So in the previous slide, we were tracing back a function along sets. Well, I'd like to make that a little bit more specific. What does it mean to actually trace back a function? So given a function, f, say between sets x and y, just take any subset of the target space, z, say. Z is a subset of y. We define f inverse of z to be the set of all points in x such that f of x is in z. And this is exactly what I was talking about before, about tracing back a function. So for example, with our favorite function, f between x and y, f inverse of 3 is just all those points that get sent to 3. So this set right here would be A and B. Okay, let's look at the set 4, 5. Okay, well, we did this in the previous slide as well. Tracing back the function along this set. Well, the only point in x that gets sent to this set 4, 5 is C. So this is going to be C, like this. Okay, and well, what about 3, 4, and 5? Well, we just want to trace back all of the points, right? So this is just A, B, and C. It's the union of A, B, and C. Okay, getting open sets involved. Now we're actually using the spaces that we've decided that we're talking about. F is continuous if for any open set in Y, F inverse of Z is open as well. So F inverse of Z is open in T whenever Z is open in T. So you'll remember that the set 3, this guy right here, is the set, the F inverse of 3 is A and B, and this happens to be an open set. And F inverse of 4, 5, which is also an open set, well, this is C, which is also in the topology. And unioning these two open sets together, well, we know that that should give us another open set, so we need to check this one as well. Well, actually, F inverse of 3, 4, 5 is the whole space X, which also has to be open in our topology. So now let's look at some examples. The first example I'd like to show you is with the natural numbers. I mean, it's the very first example we talked about of a function period. So the space is the natural numbers with the upper set topology. And remember, all that means is that the open sets are of this form, M off to infinity, or they're empty. So could be empty. But these are kind of the main open sets in the upper set topology. So I've got this function. All it does is take a natural number and double it. So I'd like to check that this is continuous. So how do we check this? How do we check continuity? Okay, so I want to take an open set in the upper set topology on the natural numbers, and I want to look at D inverse of that open set. So I want to find all of the natural numbers that actually go into this set. So you might have guessed that what we need to do is we need to try to find a natural number kind of like m over 2. So, and the reason why we actually care about this this natural number, m over 2, if it is a natural number, is because, I'll put this in a little thought bubble down here, D inverse of m off to infinity should really just be, well, m over 2 off to infinity, right? Okay, well, this works for certain if m is even. Since if m is even, m over 2 is also a natural number, and we can actually form this open set. But what if m is odd? So in this case, we can actually find a natural number say k, such that m is equal to 2 times k minus 1. And if you don't believe me, well, I mean, you can look at m over 2 and just take the smallest integer, which is larger than m over 2, and that actually gives you this k right here. Well, if m is odd and m is equal to 2k minus 1, then actually d inverse of m off to infinity is equal to, well, you guessed it, the interval k off to infinity. And so this function is continuous, since the inverse image of every open set is also open. Let's look at this example. Is this function continuous? Doesn't seem like it. So why doesn't this function seem continuous? Well, in math class, you've probably heard that drawing graphs of continuous functions, what that actually consists of is just taking your pen, putting it on the page, following along the curve, never taking your pen off the page. So continuous functions you should be able to draw without taking your pen off the page. So that seems to be a problem in this situation. But let's make the problem a little bit more explicit. I'm actually going to check that the inverse image of an open set is not always open. So remember, the open sets in the real numbers on the real line are open intervals. So I'm going to start with, say, this number right here. Just good old 0.5. And this number right here, good old 0.3. And those are approximately 0.3 and 0.5. 0.5. I'd like to check that f inverse of this open interval is also open. But as we'll see, it's actually not. So let's take a look at all of the points on the function in the graph that lay somewhere between 0.3 and 0.5. Let me make this a little bit clearer. Like this. Okay. So remember, this interval does not contain 0.5, and it does not contain 0.3. It's all the numbers that are strictly between the two. Following back the horizontal lines to check which points actually come from that interval, we see that, well, the first point that comes from this interval is actually, well, it's 0.5. And actually 0.5 is in this inverse image because f of 0.5, remember, is in this open interval from 0.3 to 0.5. It's about 0.4, just a little below that. So this 0.5 here is actually in this interval. Okay, but like I said before, 0.5 is not in this interval. And so actually there's a hole right here. Okay. And this is where the problem is. So the inverse image of 0.3 up to 0.5 is some half-open interval. And I'm going to just call this number right here r. It's a half-open interval from 0.5 to r. And actually, this is not open. Now, since the inverse image of an open set is not always open, well, f is not continuous. All right, now it's your turn.